Um, Hello everyone, and this is my fourth video. Welcome back to Scrap Paper and Philosophy. And I would like to start by apologizing. I had some brain farts last time. So this is what I want to talk about now is clear up a few things. And the first one was, let's see. Uh, The first one is that I said the Schrodinger equation was unpronounceable, and that's a lie. At some point I wanted to say Schrodinger equation, and I forgot. But the other thing was a little bit more egregious. I forgot the spring mass system when discussing kinetic energy, and what is worse, I forgot the formula for energy. Remember, um, energy over distance equals force. Uh, Multiplying both sides by distance, energy equals force times distance. And what that means is that energy equals the integral of force over space going from S1 to S2. And what we mean by space here is the three-dimensional space, right? And so, and that's why the Schrodinger equation, that's one of the reasons why the Schrodinger equation gets messy. But we can discuss that too. And well, the other brain fart I had is that really, I mean, this is I'm pretty sure this is what Newton said, that the derivative of momentum with respect to time equals zero. So for some reason I was insecure about that. Um Anyway, so let's start with this right here. Uh, there's no negative numbers in nature, and it's the passing of time that allows the concept of decrement. And so I might as well start talking about the Schrodinger equation a little bit. The wave function is this, right? It's a function. It has a real part and an imaginary part, and it's a function of these four variables, x, y, z, and t. Except there's something really similar about these three variables that distinguishes them from time. That's going to show up other places, but right now, let's just say the Schrodinger equation takes in this function, right? And it does some operations on this function. And without the linear algebra, just the calculus, okay? Well, what are the operations? Well, one of them, and to do the and to think of this in terms of calculus, it's easier to just say this, right? It's a function of one dimension of space and of time, and one of the operations we're going to do is this. We're going to take the second derivative with respect, the notation xx is so much easier, which is partial derivatives, which is what we should be using anyway. So the second derivative, right, little x of this function with respect to space. But the other operation we're going to be doing is this. It's the first derivative with respect to time. There's one operation that's going to be multiplied by I. and it's this one right here. So when we when we differentiate the wave function with respect to space twice, we treat this one way in the equation. But when we differentiate with respect to time once, we multiply it by I, the square root of -1. And this is what I'm getting at, because I think that the Minkowski coordinates at some point, uh, what I mean by Minkowski coordinates, I think that on the coordinate system, usually we multiply the time coordinate by I, so that the theorems work out. And at this point, if you already multiplied time by I, uh, and then you're taking a derivative of coordinates that you already multiplied by I, or have you? I don't know. So that's something I want to look into. But supposing you have a quantity, right? And you multiply it by I and then by t, by time. So then you multiply this quantity by I again. That's when you get a negative number. So there's two sides to an equation. You could always get a negative number by subtracting one side from the other. But I just think that little tricks that you can play on equations are one thing, and we can separate this from the actual physics. But what we can't really get away with is just saying that this orders the entire universe, x, y, z, t, and then the real part of the wave function, and then the imaginary part of the wave function. If this right here, if this orders the entire universe, uh, we have to realize that what we actually do in engineering school is we solve this for a hydrogen atom, right? And I think the eigenvalues are significant in that they have something to do with the energy levels of anyway, the mathematics works out beautifully to show the quantization of the hydrogen atom. And that's why solving it for the hydrogen atom is so interesting. But once we solve it for the hydrogen atom, what do we accomplish, right? We know what the shape of the wave is for the entire hydrogen atom. But then we can say something, well, no two hydrogen atoms are alike, which is absurd, right? All hydrogen atoms are alike. But then we can say something like, well, no, this hydrogen atom is different than the other because this hydrogen atom is in a different location, and the way we can tell one hydrogen atom apart from the other is that it has. You see, that's the thing. Is the hydrogen atom a barrier from the rest of the universe, because the wave functions a continuous quantity, right, through the whole universe. It's just an ooze, right? And so that's very mysterious. But the good news that I can give you is that the postulates of special relativity are a lot simpler, and uh, and that's where I can really make some headway into discussing what seems like outrageous claims, which I believe to be true, and so forth. So, thanks. See you next time.